How can we see 46 billion light years away when the universe is just 14 billion years old? Shouldn't we just be able to see 14 billion light years away? Hold on to your telescopes for the next few minutes while we try to understand it. Let's kick off our cosmic journey with the Big Bang, the universe's explosive birth, around 14 billion years ago, setting the stage for everything we see today. Imagine this moment as the universe's first heartbeat, sending ripples through the fabric of space and time. Now, when we talk about seeing far into space, we're also looking back in time, seeing light that has traveled billions of years to reach us. And how far away can we see? Well, let's start with the first option. That's option A. This is the simplest answer, and it's the one that most of us would intuitively give. So, if light travels at a constant speed, the longer the universe exists, the longer we wait, the farther we can see. As we currently think the universe was formed around 14 billion years ago, although new studies talk about 27 billion years. We'll make a video on that in the future. It's only logical to think that we can see 14 billion light years away, subtracting the time it took for stars and galaxies to form after the Big Bang. But this approach is wrong, since it doesn't account for everything. So you could think like option B. The option B adds a twist. Not only is the universe filled with objects emitting light, but these objects can also move relative to each other. They could move at speeds close to, but not reaching, the speed of light. This idea suggests that we can observe objects that are currently at almost 28 billion light years away if they started moving from us at nearly the speed of light right after the Big Bang. However, we still see them as they were 14 billion years ago, even though they are now almost 28 billion light years away, and we cannot see them as they are today. But again, this is incorrect, since this approach doesn't account for everything. Finally, we have option C, which increases the level of complexity, and for now seems to be the correct one. To give a better understanding to this answer, let's start with Edwin Hubble. Back in the late 1920s, he first noticed something astonishing about the night sky. The further a galaxy was from us, the faster it seemed to flee, which seemed to confirm that the universe itself was expanding. But how did he determine that? Imagine you're standing on the sidewalk and suddenly an ambulance passes by. As it approaches, the siren's pitch climbs higher and higher, but once it's speeding away, that siren drops to a lower drone. This change in sound frequency, based on the movement of the source, or the observer, is known as the Doppler effect, named after Christian Doppler, who introduced the idea back in 1842. It shows us how waves behave differently when they're in motion, relative to us. Now let's take this concept to the stars. Just like sound, light waves can also stretch or compress. If a star heads our way, its light waves get squished together, making it appear bluish, which we call blue shift. But what if it's moving away? Then the light stretches out, turning red, and hence the term redshift. Now you can also think about the redshift this way. Imagine the space as a balloon, and the light as wave painted on that balloon. If the balloon expands, then the wave gets larger, which would correspond to a redshift. If it contracts, then the waves get shorter, which would correspond to a blue shift. Although this could also just mean our distance to it is decreasing. Anyway, redshift is a crucial clue in understanding if the universe is expanding. When we see stars and galaxies in the far-off cosmos redshifted, it indicates they're moving away from us, telling us that the space itself is stretching. The more distant the star, the stronger the redshift. So in very basic terms, this is how Hubble confirmed the expansion of the universe back in late 20s. And not only that, but this discovery also revealed that the universe was expanding faster than the speed of light. Now, let's pause here for a second. You might think, doesn't this break the speed limit set by light? Well, while nothing can go through space faster than light, there's no speed limit on how fast space itself can stretch, at least for now. But let's get back to our original question. How can we peek at galaxies that are 46 billion light years away, even though the universe is just a teenager around 14 billion years old? As we've mentioned before, the universe is continuously expanding, kind of like a balloon inflating larger and larger. This means the space between everything in the universe is stretching out. We know this expansion is happening because of something called redshift, which we previously explained using the Doppler effect analogy. This effect helps us understand how the wavelengths of light stretch as the universe expands, similar to how the sound of a siren changes as it moves away from us. So, with that in mind, it's interesting to note that while the universe itself is around 14 billion years old, the observable universe isn't just 14 billion light years in radius. It's actually way bigger. Without getting into the complex math, let's just say that when we account for the expansion of the universe, it spans to about 46 billion light years in radius. Now, about the farthest light we're seeing today. It was first emitted shortly after the Big Bang, around 14 billion years ago. Interestingly, this light was originally just 42 million light years away from us when it started its journey. You'd think it would have taken about 42 million years to reach us, right? But no, because of the universe's expansion since the Big Bang, it actually took that light 14 billion years to get here. So, the farthest light and stuff we're observing now appear to us as they were 14 billion years ago, not as they are today. They were initially just 42 million light years away from us back then, but during their 14 billion year journey, the space between us and them expanded. That original sphere of space, which had a radius of 42 million light years, has now stretched out to about 46 billion light years in radius, or 92 billion light years in diameter. Wow. Yes, we know it's rather confusing, but also mind-blowing. That's our universe. And finally, there's this last question you may be asking. If our observable universe is a sphere with a diameter of 92 billion light years, that's just the observable universe. But how big is our universe in reality? Does it end there, or is there more? How much more? If you want to know, click on this video. Or if you want to learn more about the possibility of infinite versions of yourself, click on this other video. Thanks for watching.